Okay. Good evening, all of you. This is Gayatri Shirsagar from Pune Knowledge Cluster. Welcome to the 8th session of the Exoplanet course. Today we have with us Dr. Sujan Sengupta, who will be talking us about exoplanet characterization, brown dwarfs and hot Jupiter atmosphere. And we also have with us Dr. Ravi. Welcome, Dr. Ravi. So we request Dr. Ravi to introduce Dr. Sujan. Thank you so much.
Thank you, Gayatri. So welcome, everyone. We have Professor Sujan Sengupta from Indian Institute of Astrophysics. And Dr. Gupta is really an expert in exoplanet atmospheres and brown dwarfs in particular. And I've actually read his work like before. So without any delay, I'd like to invite Dr. Sujan to please go ahead and start the lecture.
Good afternoon, everybody, and thank you, Ravi. It's a pleasure for me to get this the invitation and to present some of the exciting aspect of astronomical research and discoveries to you. I will be talking about exojupiters. Exojupiters actually by now means hot Jupiters, and their big brothers, brown dwarfs. Now this is solar system, the parents of which is Sun, and in this solar system we have quite a few kind of planet, including a Jupiter gas giant planet like Jupiter, Saturn, Uranus, but they are cold giant star or cold Jupiter, and we have rocky planets like Mercury, Venus, Earth, and Mars. We are sitting over here, and which is a rocky planet and so far known as the only habitable planet in our galaxy. But about 2500 years ago, Greek scholar and philosopher Aristotle suggested that the earth is a unique place and it was the center of the whole universe. This was Aristotle's opinion based on his realization of the surrounding world and not based on any scientific evidences. That's why we call it Aristotle's philosophy. 100 years after the birth of Jesus Christ, Ptolemy supported this geocentric worldview, and he gave a mathematical description of Aristotle's view, and the Roman Catholic Church adopted the view and decreed that any opposition to Aristotelian view would be against the religion. Thus the plurality of the world was completely lost. Religious ceremony cannot stop progress of science for a long time. The evidence collected by various scholars started contradictory Aristotelian view. Just before his death in 1543, Polish mathematician and astronomer Nicolaus Copernicus published his theory that the world is actually heliocentric and the earth moves around the sun. Now, Giordano Bruno openly advocated the Copernican theory. He further suggested that all the light in the night sky are similar to the sun and they too have planets around them and those planets may have life. For such revolutionary opinion, Bruno was burned alive in the street of Rome on 14th February 1600. In the meantime, astronomer Tycho Brahe collected a large amount of data on the position and the motion of the celestial objects, and based on this astronomical data, Johannes Kepler derived 3 laws for the motion of the planets around the sun. At the same time, by using the newly invented telescope, Galileo Galilei also observed the celestial objects and discovered the moons of Jupiter, and he too supported Copernican theory. Thus the plurality of the world was re-established. The eternal curiosity of mankind about alien rekindled, and we again started asking if we are alone or if anybody out there. Moreover, the curiosity about whether planets like the solar system planet exist outside the solar system or around stars other than sun again rekindled, and there was somewhat scattered search for planet around the star other than sun, but all was in vain, mainly because of the absence of photographic plate and the photography, and finally in 19th century. So Captain William Stephen Jacob, who was an English astronomer, who was the director of the Madras Observatory from 1848 to 1859, reported in 1855 the presence of a planetary mass object in orbit around a star system, a binary star system called 70 Ophiuchi. This was done by Madras Observatory, which was shifted to Kodaikanal Solar Observatory in 1899. The institute where I work, Institute of Astrophysics, is then built out of the Kodaikanal Observatory. So, Indian Institute of Astrophysics origins from this Madras Observatory. Of course, after the report published by Captain Jacob, astronomer from Chicago University and others supported his claim, and for 50 years it was believed that this was the first planet predicted, at least. But then when better and better telescope was available, it was found that Captain Jacob didn't consider the atmospheric effect accurately. Actually, he used a small telescope, 6-inch telescope, and there was no calculator, nothing was there. Nevertheless, at that time, such type of idea revolutionized, and it has encouraged and inspired many astronomers, although now even the NASA recognize it as the first false alarm for exoplanet. And after this first false alarm by Captain Jacob, there was various attempts, almost all were the astrometry effect, that is in the binary system, where the motion of the star was carefully noticed by photographic plate, but it turned out that all were false alarm. Finally, in 1995, the confirmed discovery of an extrasolar planet around a solar type of star 51 Pegasi was confirmed, and this discovery by Michel Mayor and his colleague at that time, Didier Queloz, has been awarded Nobel Prize in 2019. Incidentally, on the same year, 1995, another object that which was considered as the missing link between stars and planet, and these are predicted by an Indian American astronomer Shiv S. Kumar in the 60s decade of last century, was also discovered. And first, so I will tell you about this brown dwarf. What is this brown dwarf? So this, remember that this was predicted in 1900, in 60s decade, sometime in 1963 or 64, but then because of the absence of proper telescope or observation, they were not discovered until 1995. Now, Shiv S. Kumar gave the name of this object as black dwarf, but since black dwarf name was already given to the end product of white dwarf, which is the ultimate fate of our sun or sun-like star, so this was later on named as brown dwarf, because they emit copious amount of infrared radiation, which is in the wavelength wise is longer than the red light. So now the first confirmed brown dwarf was Gliese 229b. Actually, there was another brown dwarf was reported, that was Tide 1, but Tide 1 was not out of ambiguity. But this brown dwarf Gliese 229b, which was a binary companion of a red dwarf star, Gliese 229a, was first discovered by Palomar Observatory scientists, and it was later on resolved, and better picture was taken by Hubble Space Telescope. Now, how it was confirmed that it was a substellar mass object or brown dwarf, or it is not a star? Because it was found that its effective temperature is between 800 degree Kelvin to 1200 degree Kelvin. Now, no star can have temperature less than 1800 degree Kelvin. The estimated luminosity of this Gliese 229b was 6.4 into 10 to the power minus 6, the luminosity of the 6 times the luminosity of the sun. Now, no star can have luminosity less than 10 to the power minus 4 times the luminosity of sun. And the estimated mass of this object was 30 to 55 times the Jupiter mass, and no star can have mass less than 80 times the Jupiter mass. I will come to that. But finally, which was the confirmation without any unambiguity came to the spectrum. There was a clear signature of methane in the spectrum. So methane, molecule like methane cannot be available or cannot be produced in any stellar atmosphere or where the nuclear burning already took place. So you can see that the signature of methane confirmed that this was not a star, but rather it is a failed star. So brown dwarfs are considered to be a failed star. Now, after the discovery of the first brown dwarf, Tate and Gliese 229b, there are a large number of brown dwarf discovered. We too, by using our Chandra telescope at Hanley on board the Indian Astronomical Observatory, has taken the image of a bright brown dwarf called 2MASS J0036. Here you can see that out of all the blue lights, this is the brown color object, which is a substellar mass object. Now, what is this brown dwarf? Now, we know that a star forms out of the collapse of a huge interstellar cloud. So, the huge interstellar clouds which are extended light years are basically static, but because of the some nearby supernova explosion or other reason, it get perturbed. And once it gets perturbed and instability is lost, it gets fragmented. And the individual fragment, by their own self-gravitation, they start collapsing. Now, when they start collapsing, their central regions start getting hotter and hotter. So, this brown dwarfs, the mass of this brown dwarf lies between 0.11 solar mass and 0.84 solar mass. That means within 13 Jupiter mass to 80 Jupiter mass. So these brown dwarfs are more massive or heavier than 13 times the Jupiter mass, but less massive than the 80 times Jupiter mass. But why this? How this mass limit comes? That comes from the nuclear burning. We know that the source of the continuous source of energy of any star is their nuclear burning. So what happens in a regular star? That under the temperature, the high temperature and pressure in their core, two proton combines to produce a deuterium, and this one deuterium is immediately hit by another proton to produce a helium-3 isotope, a type of helium. So this procedure, which is called the deuterium burning, needs temperature about 3 million degree Kelvin, which is possible only if in the core of the object, only if it is heavier than 13 Jupiter mass. Now, if the object is heavier than 80 Jupiter mass, then its core temperature exceeds 3 million degree and it becomes 10 million degree, and then this helium 3 isotope, it also fuses with one proton and produces a stable isotope of helium, that is the helium-4. So if a object is heavier than 80 solar mass, then this procedure continues and the nuclear burning continues throughout its lifetime until it exhausts all the hydrogen in its core. So therefore, the object, this brown dwarf, they are in between the stars and the planets, because in a planet even this deuterium burning is not possible, but here in the brown dwarf case, it initiated the nuclear burning, it started burning deuterium, the deuterium fusion, but it failed to ignite the helium-3. Then helium-3 is a very unstable atom, so it again emits another photon and then becomes to deuterium back. So thus by definition, or we distinguish the brown dwarf, but this is not a very sharp limit. It depends on the metallicity or the composition of the object. So depending on that, it may the mass range can vary, but roughly for solar type of star, the brown dwarf is between a 13 Jupiter mass and a Jupiter mass object. Now, the new detailed numerical simulation tells that the way a star was born, object less massive or object lighter than 13 Jupiter mass can also be born. So we are not sure what we will tell. These are all planetary objects, because we know that if the object is lighter than 13 Jupiter mass, even deuterium cannot burn it. But they might not have formed by the usual planet formation method. They form just like a star is formed. So people term as a sub-brown dwarf. So this sub-brown dwarf, it was considered that it can exist between two Jupiter mass object to 13 Jupiter mass object. So the planets are formed in a different procedure. Planet forms out of the protoplanetary disk. So once the star is formed, it has the remaining material as a disk, which is the protoplanetary disk, and in the protoplanetary disk, the gas that creates and then produces the gas giant, and then the remaining dust particle, they produces the rocky planets like Earth, Mars and Venus. But the stars are formed out of the collapse of the cloud. So brown dwarfs and the sub-brown dwarfs, they are formed through the same way a star is formed. So that's why they are called either brown dwarf or sub-brown dwarf. So you see that the sub-brown dwarfs are, there is a overlapping in the mass of the sub-brown dwarf and the planetary and the planets like our Jupiter. So that's why we call them in the outside solar system the planetary mass object, instead of telling that they are planet or they are sub-brown dwarfs. Now, this was binary. In my left side, there is a binary brown dwarf, which was Lumen 16b, and in my right side, there is an interesting object where this was the first image of a planetary mass object, where the blue one is a brown dwarf, 2 mass 1207. So the primary of this component has failed to become a star. On the other hand, the red one, the fainter one, is a planetary mass object. It has failed to become a brown dwarf. So, because the mass of the object in the primary object is about 30 Jupiter mass, which is about 30 to 50 Jupiter mass, which is much less than the minimum mass of a star. At the same time, the secondary companion is lighter than 13 Jupiter mass, and therefore it could not have ignited deuterium in its core, and so it could be a sub-brown dwarf. But we do not know how it was formed, whether it was formed like a star or it was formed like the usual planet formation. So that confusion still remains unless and until we see more and more such type of object. Now the surface gravity of this object brown dwarfs lies between 30 meter per second square to 3000 meter per second square. There is a wide range. So the size of brown dwarf is almost the same of our Jupiter or slightly bigger than Jupiter, but their mass is very high, and that's why their surface gravity is very high. On the other hand, the surface gravity of a planetary mass object is less than 100 meter per second square. So it's much less than that of the brown dwarf. Now, depending on the temperature and mainly on spectrum, the brown dwarfs are divided into 3 classes. The hottest brown dwarfs are called L dwarfs. So the effective temperature of L dwarfs lies between 1300 degrees to 2400 degree Kelvin. So here also see there is a overlapping, because the minimum temperature of a star could be even 1800 degree Kelvin. So there are many red dwarf stars which are very cool. They have 18 to 22 degree Kelvin, and therefore their temperature and star temperature overlaps. Therefore here also there is a problem to identify that which one is a substellar and which is not substellar, but a stellar object. But then in L dwarf, the clear signature of lithium-7 determines that there was no nuclear burning, because if nuclear burning starts, then lithium gets destroyed. So the presence of lithium-6 in a object, in a L dwarf or in a hotter brown dwarf, tells that it is a substellar mass object or it is a brown dwarf. Now the cooler object, the cooler brown dwarf, whose temperature is less than the L dwarfs, are called T dwarfs. So their effective temperature lies between 600 degree Kelvin to 1200 degree Kelvin. So this temperature overlaps some of the exoplanets, some of the giant planets that is discovered, which are very near to their star. I will come to that in a later stage. So these are the T dwarfs or methane dwarfs. So Gliese 229b is such type of object that is called T dwarf. Then cooler than T dwarf is another object that is called Y dwarf, and they are the coolest substellar object. Their temperature is so low that you can put your hand inside it and it will not burn. So their temperature lies between 200 degree Kelvin to 600 Kelvin. However, their classification, this L dwarf, T dwarf and Y dwarf, was actually determined from their spectrum. So now on the other hand, the effective temperature of a planet, this is effective temperature of a planet, means their own intrinsic temperature of a planet could be 100 degree to 1200 degree Kelvin. So there are planets like this one, the secondary around 2 mass 1207, whose temperature is quite high, from 800 to 1200 degree Kelvin, and that is not by the reflecting light or by the light of its primary. It is their own temperature, because it's still quiescing and it's radiating its gravitational potential energy into the heat energy. And we know that the temperature of our Jupiter has its own temperature, which is 124 degree. It has its own temperature because of its core is very hot. Now there is a systematic change in the spectrum. So when we go from cooler to cooler object, there is a decrease in the oxide. That is the signature. The titanium oxide vanishes slowly and the hydride started increasing. And so from this feature of the spectrum, we determine which is L dwarf, which is M dwarf and which is L dwarf. And then when we go to the cooler object, we get methane. And when we go to Y dwarf, then even if we get ammonia and other object, and so from the spectrum we determine which object, means which among the brown dwarf is L dwarf, T dwarf and Y dwarf. Now incidentally, so the brown dwarfs are the missing link between the stars and the planets. So because it is less massive than a star, so it could ignite deuterium, but it could not sustain the nuclear burning because it didn't have the sufficient mass to ignite it. But it is more massive, it is heavier than a planet, so that it could ignite deuterium, but it failed to ignite helium-3. So that's why it is the missing link. It is it lies in between the realm of planet, most massive planet and the least massive star. Now incidentally, our fourth neighbor, the Sun's fourth neighbor, is a brown dwarf couple, is a binary brown dwarf. These are called Luhmann 16a and Luhmann 16b. So their temperature is around, one is L dwarf, whose temperature is about 1600 degree Kelvin, and another is in the transition between L dwarf and T dwarf, so it is slightly cooler. So these two, L dwarf and T dwarf, or both are, you can tell, L dwarf, are our fourth neighbor. So our first neighbor is Alpha Centauri system, which has three stars. One is Alpha Centauri B, one is Alpha Centauri A, and around them is a cool star or red dwarf star called Proxima Centauri. Proxima Centauri sometimes becomes the nearest star to the Sun. The second nearest neighbor is the Barnard star, and the third nearest one is this lumen 16b. Now, incidentally, the fourth one is also a brown dwarf, but this is a white dwarf. This is actually a sub brown dwarf because its mass is estimated to be less than or very near to 10 Jupiter mass. So probably it could not ignite deuterium even in its core, and it is so cold. It is the coolest brown dwarf or sub brown dwarf known so far, that you can put your finger or hand and that will be frozen. The temperature of this object is less than our Antarctica's temperature. So this object was discovered by the Wide Infrared Survey Explorer of NASA, and then it was also monitored by Spitzer in the infrared, because these objects are so faint that in optically they cannot be imaged, so they are imaged in the infrared region. So these are the photograph. You can take it from brown dwarf, because brown dwarfs have enough brightness, enough luminosity, so that Earth-based telescope or spacebound telescope can detect them or can image them. Now we come to the exoplanet. That's the brother of this brown dwarf, which could be, many of them could be sub brown dwarf, or they may be planetary mass object, or they might have formed like a planet, but their mass is 8 to 10 times heavier than our Jupiter. So this picture I have shown already to you. This was the first image of a planetary mass object around 2 mass 1207. The primary is called 2 mass 1207, and the secondary object is called 2 mass 1207b, which is a sub brown dwarf or whose mass is about 10 Jupiter mass. But at the same time, there is a planetary system was directly imaged. How it was imaged? Because the planets are far away from their star, so they hardly receive their starlight, and the starlight was blocked by an instrument called coronagraph. By blocking the starlight, the photograph of the image of the 3 planets, and ultimately the fourth one, E, was taken. So this was the image of the first image of a planetary system, and this was discovered in 2010. You can clearly see that the planets A, B, C, D. So the ABCD name is given on the basis of their discovery. That is the A, if we call, that is the star, so there is no designation. B is discovered first, C is discovered after that, then although D is nearer, but D is discovered after the discovery of C, and E is discovered at the last. So these are the image, but the mass of all these planets are 6 to 10 times heavier than the Jupiter, and this entire system is quite young. They are about 50 million years to 80 million years old, so that they are still under the construction, and they are still very hot, so that they are self-luminous. Although they don't receive any significant light from their star, they are self-luminous, and therefore they can be imaged in the infrared. So similarly, there are Beta Pictoris b, where we can see a planet orbiting, and in fact we see the protoplanetary disk also, where the planet has formed. It is still there and not evolved. These are all old picture. This image was monitored for 10 years and 15 years, and even nice video was made. You can find out in NASA's website. So this is HD 95086b, another planet that is directly imaged. And here is the ROX X42b BC. ROX 42b is a binary star, so it has 3 planets orbiting the binary system. So you know that there are quite a few planets discovered which are orbiting around the binary system. In fact, the Proxima Centauri where the Proxima Centauri orbits the Alpha Centauri A and B, and Proxima Centauri has a Earth-like planet, rocky planet around it. So there are planets which are giant planets which are orbiting the binary star system. So rocks is also like that, but the planets are far away, so it can be imaged by blocking the both the stars. At the same time, Pan star in 2013, they discovered some object which are not in the binary. So they are free floating object, whether they are sub-brown dwarf or they are planetary mass object. Nobody knows that what is their origin. Either they have been formed like the star, like the 2 mass 1207b, but without any component, primary component, or they are formed like planet and then detached from the planetary stem and they are roaming around alone. So we do not know that what is their origin, but they are quite young and that's why they are quite bright, and these are all nearby. There are quite a few free floating planet was discovered which has no parents, but they are quite massive and they are quite young, and that's why they can be directly imaged. Now, these are all the special kind of giant planet. They are really giant because their size, although their size is from Jupiter, similar to Jupiter or about 1.5 times that of Jupiter, their mass lies between 6 times to 10 times that of Jupiter, and they are far away from their star so that their starlight can be blocked. But most of the planet that is discovered, you cannot, even if they are very bright, you cannot detect them or you cannot image them because they are hidden under the intense light of their planet. So for example, the 51 Pegasi B, this star in the margin here, this was so bright that you cannot and the planet was so close that you cannot detect them or you cannot image them or you cannot discover them directly like the previous one, although this could be very bright or this could be very young. So astronomers takes different indirect method. They monitor the effect of the planets on the star and then they confirm the presence of the planetary object. I think in your previous courses someone has told about the different method of discovering exoplanets. So I'm not going to that, but the most popular method through which most of the exoplanets are discovered is known as transit method, which was proposed by Otto Stoop in 1952. So imagine that it was proposed in 1952, but this the first planet discovered by using this method was achieved in 2000. The first transiting exoplanet AGT 20945b was detected. So Otto Stoop also proposed another method, that is the radial velocity method, through which Michel Mayor and Didier Queloz discovered the first confirmed exoplanet around a solar type of star 51 Pegasi b. Now this AGD 209458b was a very popular, very known planet. It is a giant planet. So this has given for the first time the detection of atmosphere in 2002. So the atmosphere, even the atmosphere of this planet was discovered, and then during the secondary eclipse, the infrared radiation was also monitored. So when the star is in front of the planet is in front of you, the infrared radiation from the planet and the star adds up, and that comes to the telescope. But when during the secondary eclipse, that is when the planet is behind the star, so its radiation is blocked by the star, and therefore there is a drop in the infrared radiation, and this drop actually amount to the infrared radiation that is emitted by the planet. So this was the second, through the infrared radiation, the amount of infrared radiation or the albedo was the reflectivity or whatever be the thing, the temperature of this planet was detected very precisely during 2005 through this secondary eclipse. Then in 2007, water vapor was for the first time water vapor was discovered in a planet, in an exoplanet. So by T. Burman, and in HD 189733b, another hot planet by Giovanna Tinetti et al. Incidentally, Giovanna is my collaborator also. She is the PI of the upcoming ESO European Space Agency's Space Telescope Ariel. So for the first time, atmosphere in exoplanet was detected. For the first time, infrared radiation was detected, and for the first time, water vapor was detected as early as in 2007 from the same planet HD 209438b. So what happened that we know this exoplanet much better than we knew the solar planet before the space exploration by Pioneer, by Voyager, all those things started. So now, using this transit photometry, we too in IIA, in Indian Institute of Astrophysics, and my group, then we monitor the exoplanet, mostly the giant exoplanet. So we use the Jagadish Chandra 1.3 meter Jagadish Chandra Bhattacharya telescope at Bainubapu Observatory in Kavalur, which is in Tamil Nadu, and also by the Himalayan Chandra telescope at Hanle, which is in Indian Astronomical Observatory. So using these two telescopes and through the transit photometry method, we take the light curve of the of quite a few planets, and then we have developed a very precise numerical code that and reduce the noise in the observed data. And because these are somewhat larger telescope, so we find their physical properties such as their size and their orbital period and their transit period, etc., so precisely that our data is considered as a default value by NASA and USA, and these parameters will be used for further probing the atmosphere or the properties or characterizing the atmosphere of many giant planets. We have also compared, analyzed by using our method by taking the TESS planet, the planet that those are discovered by the TESS satellite, the space telescope, and we compared the parameters from of the same planet by using the ground-based telescope and the space-bound telescope, and we determined that how the ground-based observation could be betterment, means could be improved. So here is another. Here the red line is taken from Jagadish Chandra Bhattacharya, the red error bar, and the blue one is taken from the Hanle telescope. Since Hanle telescope is much bigger, so we get many more points by using this bigger telescope, and it is complemented by the Jagadish Chandra Bhattacharya telescope. Now we have to probe the atmosphere, if there is any atmosphere. Even the transit method can probe the atmosphere. If we take the transit light curve in different wavelength band, then if there is no atmosphere, then the light curve, it will become constant. Like if I show this will become constant. There will be no change in any wavelength. So if there is no atmosphere, if this is a planet, is a rocky planet or nothing is, we cannot, all very thin atmosphere, then in all wavelength the light curve will remain same thing. But if we take in different wavelength, then there will be a difference, because the different wavelength of light penetrates at different depth of the atmosphere, and therefore we can get the depth of the light curve at different different amount, and we can tell that whether there is an atmosphere or not. But to probe the atmosphere, to understand the chemical composition of the atmosphere, to know the size of the atmosphere, we have to do the spectroscopy. But here, unlike the stars or the brown dwarf, direct spectroscopy of planet is not possible, because then you have to block the starlight, and then by coronagraph, by other method, and then you have to pass the planetary light. Now, first of all, if the planet is very near, then it is not possible to resolve the planet from the star, and therefore you cannot block the starlight, means and to take the light of the planet. and then the planetary light is also not very bright, or it is not very high, and therefore the spectrum is not possible. So the astronomer takes a different way, we take a different way, and we call it transmission spectroscopy. So what we do that, we send the light of the star through an instrument called spectrograph. So this, when there is no planetary transit. So when there is no planetary transit, the starlight gives a spectrum which carries the atmosphere of the star, the chemical composition of the atmosphere of the star. Next, what we do that, we take the same light through the spectroscope when the planet is transiting. So when the planet is transiting, it blocks the star, but part of the light passes through the atmosphere of the planet, and that passes through the spectrograph, and so that gives the combined spectrum of the star and the planetary atmosphere. Now if you subtract the second, the first one, that is the stellar one without transit, and from the combined spectrum you get the residual, which is the spectrum of the planetary atmosphere. So we theoretically model, but these are possible. This spectrum needs a bigger telescope and very complicated observation. But we numerically model this transmission spectra, and we also fit with the observed transmission spectra data. Those are available and which are taken from Spitzer and various other telescope in the optical and in the infrared. So here you can see that we have rightly modeled the transmission spectra, the observed data was the transmission spectra by our numerical simulation, by our model. Now for the hot Jupiters, the thermal radiation also contribute to this spectrum, to this transmission spectrum in the infrared. So that may also gives rise to the signal to the transmission spectra, and that also we calculated. So the first part of this, we included the scattering by cloud and scattering by molecules in the planetary atmosphere, and the next one, the second one, the right side, we have included the thermal radiation of the planet, the planetary atmosphere, and its contribution to the transmission spectra. Now this transmission spectra is expressed in terms of the transmission depth, which is the amount of light that is passing through the atmosphere of the planet. So here F in is the flux when the transit is occurring, and F out is when there is only the star spectrum, the flux is calculated. So this can be expressed in terms of 1 minus the right hand side, 1 minus Rp. So this is the flux that is blocked by the planet, and this is the flux of the planet itself. The planet itself, know that the light that is passed through the planet, that is the fraction of light passed through the planet, and this is the flux of the star. So this can be expressed as a term of the radius of the planet and the radius of the star. Now this radius of the planet means not only the base, the extent of the atmosphere also. So here the planet star means where you cannot, beyond which you cannot see any light from the planet. So that is the Rp, and which is proportional to the planetary flux versus the stellar flux, the ratio. But this is very complicated. You have to solve in order to calculate that AP, you have to solve the detailed radiative transfer equation with incorporating scattering, cloud, all the molecules and everything. Nevertheless, by doing all those things, we calculated this transmission spectra, which when taken and compared with the observed data can tell you confidently that what are the elements present in the atmosphere of the planet, of the giant planet. This can be extended also to the rocky planet if they have atmosphere. So this is for HD 209. We have also modeled the spectrum for another thing, which is HAT P1b, which is also a giant planet. So you can see the blue is our theoretical simulation of the transmission spectra, and the red one is the observed data available till date. So in the optical, our new thing is that we have incorporated all the physics behind it, that is scattering, cloud and everything, and the thermal radiation also in that case. So the first it is the photometry that detects and tells the properties, that is the size of the planet, that is the period of the planet, and in fact, if you know the radial velocity, you can calculate the mass of the planet. Then you can tell the mean density of the planet by using both the method, transit method, and the transit photometry method and the radial velocity method. And you can tell from the mean density, you can tell whether the planet is gaseous or the planet is rocky. So rocky planet will have much higher density than the gaseous planet. But to understand the atmospheric composition, the chemistry, and to characterize the atmosphere of exoplanet, you have to go for transmission spectra or transit spectra, which is not a direct way, but it can be also measured. And you know that already people have done it for gas giant planet, which are very near to the star. Now, one common property of this giant planet and the brown dwarf is the formation of cloud in their atmosphere. So the brown dwarf, especially the L brown dwarf, they are their temperature is so appropriate that silicon condensates in their atmosphere. So silicate under high temperature, the silicon gets gaseous, and then it becomes droplet, and then what happens, it goes up because of the turbulent to the atmosphere, but when the object cools down, it falls rain down again, and it rain down and become the clear sky. So in the L dwarf, the surface gravity and the temperature is so appropriate that it should have all the time a silicon cloud, not the water cloud. So this cloud is made of the molten silicon, so gaseous silicon. So now gaseous silicon condensates, and it gives rise to silicon cloud. Now this type of cloud is also possible for the hot Jupiter-like planet, which are very near to their star, like HD 209 or whatever I told you, that they are also supposed to have cloud. And recently JWST also detected the transmission spectra where the presence of cloud is also included in their model. So cloud is a very important thing. Now, but cloud distribution differs from object to object. So when there is, the object is M dwarf or coolest star, and between the L to M dwarf transition, then they have a clear sky. There is no cloud. The cloud has evaporated. So temperature is so high that the cloud has, the silicon has evaporated. When the temperature drops to L dwarf, that is between 24 degree or to about 1400 degree, then the silicon clouds are situated. It appears in the visible region of this brown dwarf. Now when it cools down further and it becomes a T dwarf, that is, the temperature becomes below 1400 degree Kelvin, then methane appears in its atmosphere, but the silicon cloud, it precipitated down, it rained down, because it becomes cool, so it rained down just like our water rain, and the sky become completely clear. When it becomes further cooler and it becomes Jupiter type of thing, means hot Jupiter, I am telling, the surface gravity is different, then the ammonia cloud appears in their atmosphere. So some of the white dwarf may have also water cloud, and they may have also ammonia cloud. So Jupiter and some of the white dwarf may have the same nature of cloud. Now this clouds, the light that is either reflected or that is emitted as a thermal radiation, that gets scattered by this cloud, and that gives rise to another property of light, that is called polarization. Now these objects are far away, so when you measure the polarization, you are measuring the disk integrated, the disk average polarization. Now incidentally, these objects are quite young, and they are rotating, their spin rotation is quite fast, and therefore they are not perfectly spherical. Like our Jupiter is not perfectly spherical, it has some oblateness, which is 0.06. The Saturn, our Saturn has the, in the solar system, it has the highest oblateness, 0.1, so it is rotating so fast, and you can estimate the obliqueness, which is the ratio between its polar radius and the equatorial radius. In fact, our Earth has also a obliqueness 0.03, which is very small, which is because of rocky planet. So this obliqueness can be determined by Darwin Dada Chandrasekhar relationship. Now, because of this rotation and they are oblate, and because of their oblate, they introduce asymmetry in their disk, and therefore the disk average polarization is non-zero. So then what will be happen? Their light can be partially, their light can be linearly polarized because of the scattering of the cloud particle, and this polarization will not be completely cancelled out because of their oblateness. So one can probe the atmosphere of exoplanet and brown dwarf through polarization. Incidentally, that the brown dwarf will be polarized, the light of brown dwarf will polarized was predicted by me in 2 decades ago in 2001, and after 2 years this was confirmed by a French group led by François Ménard, and subsequently now many brown dwarf has shown polarization, and it is found that 95% of the L dwarf shows polarization. So that confirms that the presence of cloud in their atmosphere. Not only that, there are studies that the brown dwarf which are rotating faster are showing more polarization. So that is telling that the oblateness plays the important role. But the inhomogeneity in the cloud also plays a role. But before that, many of you may not know that what is polarization. So let us listen this video to know that what is polarization and why it is important for brown substellar mass object like brown dwarf and polarization, because this polarization is not detected from the ordinary stars. They are not there, except some bright star which are rotating very fast like B star, they show some polarization. Some magnetic star can show polarization, but normal star doesn't show any polarization. But the substellar mass object, because they have clouds in their atmosphere and they are rotating very fast, so they show insignificant amount of polarization or detectable amount of polarization. Although polarization from reflected planet is not yet discovered, because their polarization is diluted by their by the starlight which are unpolarized, but attempts are made to find out the polarization from directly image planet which are hot or self-luminous, and limit was put on that polarization. So let us now explain me what is polarization and why it is important.
What is polarization? Technically speaking, polarization is the measure of the anisotropy of a radiation field. Light is a wave of electric and magnetic fields. These waves can be oriented in any direction. The direction of each wave's oscillation is called its polarization. Most light sources, including natural light, produce randomly oriented waves. We call that light unpolarized. However, if the light waves are in the same direction, we say they are polarized. A device called a polarizer lets us measure light polarization. A polarizer allows light of the matching orientation to pass. It blocks light of the opposite orientation. Unpolarized light will pass through the polarizer at any orientation. Now, how does light become polarized? Light becomes polarized either by the presence of a magnetic field or when light scatters off of a surface. A properly oriented polarizer can block this reflected light. Light can also become polarized from scattering off of gas and dust particles in an atmosphere. You can see this effect in the sky by rotating your head while wearing polarized sunglasses. The amount of light that gets polarized tells us about the gas and particle properties in the atmosphere. Polarization studies have helped us understand the atmosphere of the other planets in the solar system. The unpolarized starlight becomes polarized when it scatters off high altitude haze or cloud in the atmosphere. However, if the atmosphere is uniform, the cloud is distributed homogeneously, or if the object is perfectly spherical, then the net polarization becomes zero, as the polarization in all directions cancel out. But if the cloud is distributed inhomogeneously in band-like structure, or if the object is oblate because of its rotation on its own axis, like our Jupiter, Saturn or Earth, then the net polarization becomes non-zero. On the other hand, if a planet transits across a star, or a satellite or exomoon transit a planet, then also the net polarization can be non-zero.
So this was made by my collaborator at JPL, who discovered polarization from lumen 16 AB very recently. And this is very interesting thing. When we tried to explain the amount of polarization from lumen 16 AB, which was detected by using Gemini South, and we found that the one component, that is the lumen A system, is cannot account because its rotation is not sufficiently high, so it is not sufficiently oblate. So the oblate model cannot explain the amount of polarization, high polarization that is detected. Whereas lumen B, its rotation is quite high, and so it will give sufficient oblateness, so that the polarization due to oblateness alone can explain the detected polarization. So from there we have concurred that there must be inhomogeneity in the cloud that is giving rise to the polarization in lumen 16A. Now, as I have told that many brown dwarf polarization was detected, and this was the latest thing, that lumen 16AB is showing polarization, and through polarization we can also tell about the distribution of the cloud in their atmosphere, like whether it is a band like in Jupiter. In fact, the presence of sulfuric acid in the atmosphere of Venus was also detected through polarization. Now, I have told you that there is another way object can be polarized. Suppose there is a M dwarf, very low temperature M dwarf or brown dwarf, and a star and a planet is transiting it. Then when it transits, it also breaks the symmetry and it gives rise to polarization. So this is called transit polarization or eclipse polarization. Now I predicted that because of the transit of the TRAPPIST one system, the starlight of TRAPPIST will be polarized, because TRAPPIST has about 2400 degree temperature, and under that situation it may have a very thin atmosphere, thin cloud on it, and therefore the light of TRAPPIST will be scattered and polarized, but it is not sufficiently oblate or not inhomogeneous for the polarization to be detectable. So during that, when the planet will transit it, it can give rise to polarization. And subsequently, my prediction was confirmed by a Spanish group which detected polarization from TRAPPIST 1 during the transit of TRAPPIST 1b. So now you know that how polarization arises, how polarization can be detected, and how polarization can be used to probe the atmosphere. So we get finally the last one that we did, that there could be exomoon also around a giant planet, but so far no exomoon has been discovered. We for the first time calculated predicted the light curve of a giant of a rocky exomoon around a giant Jupiter-like planet, and we showed that this can be detected. This is within the range of detectability of the James Webb Space Telescope. So because we know the solar system is full of satellites or natural satellites or moons. In fact, the Jupiter's moons, there are several moons and they are very large, like Calypso, Ganymede, even Titan. So it is naturally expected that the exoplanet also should have moon, but so far they are not detected. And we have shown that we have deduced, we have deducted, and we have calculated the light curve that gives the signature of the exomoon, and we have also shown that the JWST can detect the signature of exomoon in the transit photometry of giant exoplanet. So finally we come to the summary of this talk as the time is almost over. So we can observe brown dwarf, we can understand the atmosphere of brown dwarf very well, we can and then we can extrapolate it to exojupiters that include the self-luminous planet or directly image planet, and we can see that the only difference between, there is overlapping between the temperature of brown dwarfs and exojupiters, even reflected or self-luminous, but there is a difference in the surface gravity. Then exojupiters, we go to the smaller and the fainter object, that is the mini Neptunes or super Earth. And finally, the final aim, the final goal of mankind is to find out the exo-Earth or the rocky planet in the habitable zone, or a habitable moon, or a rocky moon in the habitable zone of a giant Jupiter or a exojupiter. So this, all these methods systematically we do by using three methods: photometry, then spectroscopy, and then finally polarimetry. So I am sure that very soon our upcoming telescope JWST already functional, and there will be many more telescope will come which will even probe Earth-like rocky planet in the habitable zones and its atmosphere. And photometry, spectroscopy, and polarimetry, by using all these three methods, we can detect one day the biosignature in some of the planets or in some of the moons, and then we can answer the eternal question of mankind: is anybody out there? So if you want to know more about all these planets, you can please collect my book written for as a popular book without any technical term. It's called Worlds Beyond Our Own: The Search for Habitable Planet, published by Springer, or you may ask your library to get this book from Springer. Thank you.
Thank you, Professor Sujan Sengupta. We can, request participant to ask question either in the chat box, or we have changed the settings so that participant can raise the hand and they can ask question directly to Professor Sujan.
Yeah, I think if they ask it directly, that will be better, because otherwise I have to follow the chat box.
Sure, sir.
So in that case, I will request you to read the chat box and I can answer it.
Yeah. I can do that. But if participants, if you have any question, please raise your hand so I can unmute you. I think there are a few questions. We can take that first.
Yeah, go ahead with that. See, no question, don't worry about that. No question is silly question.
So Arpita Saha asked that, which software did you use for this modeling and plotting?
Well, we have developed our own software, but it is Python based. I am quite an old guy. I have started all this business 30 years ago, and it was radiative transfer. So at that time, the basic code was solving the radiative transfer was made by Fortran only. But then, as the time goes, my PhD students, they have converted all those Fortran codes, Fortran programming, into Python programming. And these are all solving the very complicated integral partial differential equation with several matrices, multiplication, and everything is there. There are many procedures to solve this radiative transfer equation to prove the atmosphere. So these are basically Python based code, and the photometric analysis is also made by Python code. And noise reduction code is already in GitHub in public, and we'll make the transmission spectra code also public.
Thank you, Professor. So there is another question by Sanjay Baliwal. He is asking how much precision is required for finding an exomoon around the eco-Jupiter in polarimeters?
Polarimeters, I have not told that the exomoon can be, that is extremely difficult. There is no, so far we have not detected exomoon. So forget about spectroscopy or polarimetry. So the precision is needed that I have to share. I have shown you in the picture. Let me show it again. So can you see this picture?
Yes, sir. We can see that.
Okay, so you can see that this is quite small, but still can be detected not by Hubble or any ground-based telescope. Probably upcoming 30-meter telescope ELT can do it. So we need more light. So there is a, if this is the below, this one is the transit, the light curve, the light reduced by the starlight reduced because of the planetary transit, and the smaller one here, it is the light blocked by the moon. Where is my cursor? Yeah. So this is blocked by the moon. So you have to detect this one. Now if you have a smaller telescope, this will be smaller and this will be so smaller that it will be flat and you cannot reduce it. So we have estimated, so you can see here that 9 point, these numbers are there. So if you want to know the details, then you can go to our paper, that is Sengupta and Saha, published in FJ already, and one more paper is in the Nature Science, where we have told that why only exomoon, even exomoon in the habitable zone can be in the reach of 30 meter or ELT, or even marginally by JWST. So the signal is very less, okay, but bigger telescope can do it, and spacebound telescope will have the preference for that.
Okay. Thank you, sir. And there is a question by Bruno. He's asking, can brown dwarfs host giant planets? And can planets around them have any substantial atmospheres?
Very good question. So, so far, I have shown one object, that is the first image of a sub brown dwarf or a planetary mass object, that is 2 mass 1207. Through gravitational microlensing also, quite a few planet was discovered around brown dwarf, but so far there is no planet is discovered through transit method around the brown dwarf. So because brown dwarfs are very faint, you need a larger telescope and lot of nights are there. So there are projects to detect a planet. In fact, it depends on the mass of the protoplanetary disk. Since brown dwarfs are very light, so its protoplanetary disks will be very light because it may not have much amount of matter, and therefore it cannot have giant planet. It should have only rocky planet formed through planetary disk, protoplanetary disk. But those are not yet detected, but there is no problem that brown dwarf will not have planet. But it is a difficult observationally, and we hope that rocky planet will be discovered around brown dwarf in near future. There are many projects that are going on, but there is so far no dedicated telescope. That is another thing. And what was the next answer? That where are the atmosphere? Yes, planet around brown dwarf can also have atmosphere. There is no problem for that. In fact, they may also be a habitable planet around a brown dwarf. So all those things are theoretically possible, but so far we have not yet detected such type of thing.
Thank you, sir. There is a question by Rajvardhan Karle. So he's asking, how do I access James Webb telescope data? And also he's asking, what happened if two brown dwarfs collide?
It is very difficult for two brown dwarfs. See, first question, JWST, you can ask to Ravi. The data is public after some time, and that is called Mars web server, where you can download it. But if you are not, you won't get like this curve. So this will be the raw data you have to reduce. So you need proper training and hard training to deal with those data. So just getting the data will not tell you that you have discovered something. You have to reduce those data and then only you can tell. Those data JWST, some of the data are available, data are coming, and they are becoming public. The second question is that collision of brown dwarf. No, they are far away. They follow the Kepler's law, so there is no chance of they will collide, because for collision they need to lose their rotational energy. So just like two binary stars never collide, so two brown dwarf will not collide.
Okay, thank you, sir. There is a question by Bruno again. So he's asking, are brown dwarfs more active than M dwarfs, and how does their magnetic field affect habitability?
So that's also good question. No, brown dwarf are much less inactive than M dwarf, and you have asked the opposite question. I think you have heard the information correct, but in a wrong direction. The magnetic field of M dwarf is about 1000 Gauss, much higher than the Sun even, and brown dwarfs are almost neutral. They don't have any charged particles, so their magnetic field is very less, and so their activity is also very less. A few brown dwarf has shown X-ray emission, but those may be because of some other incident or some exceptional cases. But in general, the brown dwarfs have not developed any strong magnetic field, because its atmosphere, or it is highly neutral, because its temperature is very low, so there is no ionization in the matter, and therefore the magnetic field has not formed even by generator or something like that. It is not there, so there is no measure. Whatever measured has been done for some brown dwarf, high magnetic field was found, and polar activity was found, and X-ray also found in some part, but these are all particular case. On the other hand, M dwarfs are abnormally active, so it emits much frequently the flare and ultraviolet rays, all those things, because it has a magnetic strong, so 1000 times higher than the magnetic field of the Sun. So you have got in the other way around. Brown dwarfs are very less active, and it has a very weak magnetic field. There is no, so far there is no general evidences of strong magnetic field, and all magnetic field. It has seen flare activities and many things, and they are very highly activated. Like our Proxima Centauri is a M dwarf, and it is a very active star. So therefore, even if the planet is in the habitable zone, which is rocky and temperature appropriate for water to exist in liquid form, but because of this frequent flare and frequent activity and intense gamma ray and ultraviolet ray, life may not be possible. Even the atmosphere may not be possible. It may be destroyed by these ultraviolet rays of the Proxima Centauri, which is a M dwarf or red dwarf. Okay.
Thank you, sir. Bruno, do you want to unmute yourself and ask question directly, or? I think, yeah, we can go ahead with the next question. So Megha Mishra is asking, is the age of the first brown dwarf and the first stars in the universe comparable, or are brown dwarfs relatively new objects in the universe?
No, brown dwarfs are old objects, but brown dwarfs generation star, they are also formed like our Sun. So when we get other molecule like oxygen, heavier molecule, that means that it was formed not very early, but recently. Their second generation, their age may be 4 billion to 8 billion years, but they will survive for a very long time. The very long time they will survive, because they don't have any nuclear activity or anything. So ultimately their temperature will reduce, and they will become fainter, and they will become completely faint, and you cannot detect them, because it is the gravitational potential energy that is getting converted into light energy and thermal energy, and so this energy is not unlimited. One day it will be almost finished, and you won't see this brown dwarf, but that takes longer time. The fainter is the star, its longevity is much higher. So a M dwarf, like a red dwarf, a Proxima Centauri, it will last for trillion of years, whereas our Sun will last for maximum 10 billion years. So it is like that. So if the if the star is less massive, it is less bright, and so its nuclear activities are much less, the rate, and it lasts for much longer time. So brown dwarf and M dwarf will last for much longer period than our sun or a sun-like star. But they are formed almost same time. 4 billion years. Some brown dwarfs are quite young. Some brown dwarfs are 8 giga year or billion years old. Like that, it varies. The age varies, but they are not in the beginning of the galaxy. I mean, they are not the first star. The first stars are made of hydrogen and helium. Okay, then inside them, hydrogen and helium, there was nuclear burning, and so higher material like oxygen, nitrogen, all up to iron was formed. And then when they exploded in a supernova, then during that time, gold, silver, all those things was formed. Now this material, which was synthesized inside a star, first generation star, was distributed in the interstellar medium. Then this interstellar cloud again collapsed by their gravitational self gravity, and they formed the second generation star like the sun, and therefore the sun has the heavier matter like oxygen, nitrogen, all those things. So in the beginning of the universe, only there was hydrogen, helium, and a little bit of lithium. All the other things was formed inside a star. Even the carbon in your body was synthesized inside the star. So that's the relation between you and the star. And when you will die, your carbon will also mixed in the earth, and the earth will be destroyed. It will be distributed its matter in the interstellar matter medium. New star will form out of that, and then new planet will born. There could be Earth-like planet. There could be life again. So it is just a recycle of the material.
Thank you, sir, for the answer. Bruno, you can ask question directly.
Hi, I just wanted to ask, what do you think? Could there be new types of planets around
New what?
brown dwarfs? Can there be any new type of planets orbiting brown dwarfs?
No, I don't understand your question. See, brown dwarf, new type of brown dwarf. Brown dwarfs are classified by their mass means by their spectrum, and so we know that the limit, the upper limit and the lower limit of their mass, like 13 Jupiter mass roughly, and 80 Jupiter mass, where deuterium can burn, can ignite, and helium-3 can be generated, but they cannot continue the nuclear burning because it will finish, it will not go to helium-4, the stable isotope of helium, so it will not continuously produce nuclear energy, and the nuclear burning will stop, and it will ultimately become cold. It is an energy, the light will be only emitted from the gravitational, the potential energy, that is because of the contraction and the heat in their core. And sub-brown dwarfs are brown dwarfs where even the deuterium, the mass is so less that even deuterium burning was not also formed. Now there is a overlapping between this mass of brown dwarf and the giant exoplanet, because you are not going to see how a particular object was born. So the only thing is to evolution of that object and to tell that, but then evolutionary model is also in problem because we do not know the initial condition. But so far we know L dwarf, T dwarf, and Y dwarf. There cannot be another thing, all those, because this all covers the wide temperature from 24 degree to 200 degree Kelvin, and which overlaps with the exoplanet. Even our Jupiter temperature, its own temperature is 124 degree. So it's like that. So there cannot be new type of thing, but new type of exoplanet certainly be there. We do not know. See, before the discovery of these exoplanets, we thought that our knowledge on the planet is complete because we know solar system only. We didn't know mini Neptune. We didn't know about super Earth. We know so many kinds of planets that our concept on planetary science has revolutionized. And we now understand that we didn't know anything. much from the solar system. Maybe the solar system is an exception. So here the rocky planets are near to the star, giant planets are far away, but most of the planets discovered yet, where the giant planets are very near. So our Jupiter is a cold object, but most of the Jupiter, that is exo-Jupiter, that is discovered, are very hot Jupiter. Even some of these Jupiters are found to be losing mass because of their high temperature. Then there are mini Neptune, which are intermediate to gas planet and the rocky planet. Maybe they have a rocky core, but their atmosphere is very high. There could be a water planet. There could be diamond planet. There could be many type of planets, and of course new kind of planet could be discovered. But the ultimate goal of this field is to find out another Earth, a twin of Earth, where the biosignature can be detected, so that the eternal curiosity of human being, whether life exists elsewhere, whether we are alone or if anybody out there, can be answered. So now all the focus has gone to detect the rocky planet in the habitable zone, and then to detect their atmosphere and to find out, to discover biosignature in their atmosphere, to tell if life is common in our galaxy or it is a special case on our Earth.
Thank you, Professor. I think there is a last question. Will India or ISRO launch a space telescope dedicated only for exoplanet? This is a question by Raghav Narsimha.
There is a proposal. The planet is called the proposal. The project is called ExoWorld, where it is proposed that a 1.5 meter telescope will be launched, but I am not sure about the current status of it. So there is a proposal in collaboration with Nikku Madhusudan of Cambridge University, and these are being done by the people at the Trivandrum Institute in Indian Space Science Institute. And so this project is called ExoWorld. So there is a proposal for India to launch a satellite or telescope entirely dedicated for exoplanet. But I'm not. I don't know much about its progress, as I am not in this project, because I don't belong to ISRO. No? So I am a free citizen of a free institute. So you may ask the ISRO people who can tell you about the present thing there.
Okay. Thank you, Professor. Does any participant have any question?
The chat box, there are 25 messages being seen, right?
Yeah, so we have covered almost all questions.
I see. Good.
I mean, they are only saying thank you, and that's why it is.
Oh, I see.
I didn't. I also.
Yeah. I didn't see it.
Yes, sure. So if there is no question, we can close the session, sir. Thank you once again for joining this session, and thank you for showing us wonderful videos and simplifying the concept. And we request participant to join us tomorrow again at 4:30. And Dr. Ravi, do you want to say anything?
So I want to first thank Sujan for a super excellent talk. To be honest, I also learned a little bit of something from about brown dwarfs. So thank you so much, Sujan, for giving this talk, and we will make the talk available at some point to everyone. Could you also please organize this kind of introductory course for GR, someone Meghna? That we will talk with Dr. Kembavi about the GR course, and then we'll get back to you. But however, we will thank again Dr. Sujan, Professor Sujan again. Hope to see you.
All right. It's better to have be generally. So just please wait for a second. I will take a screenshot of this before you close it. Okay. So just 2 seconds. Yes. Thank you.
All right.
Thank you so much.
Thank you so much. And we will see you all tomorrow, right, Gayatri, at 4:30 with Joy Montorio, Professor Joy Montorio from ISET Pune, talking about climate models.
Yeah. Thank you so much. Thanks a lot.